Right now, 5 to 7% of every watt of electricity generated in the United States disappears before it reaches your home. It turns into heat inside the power lines. That wasted electricity could power over 20 million homes every year, for free. The power lines delivering electricity to your home right now are the same fundamental technology Thomas Edison used in 1882. Copper or aluminum wire, simple resistance, the same basic physics. We have improved cars beyond recognition in that time. The grid, mostly the same wire. But underground in Munich, in Essen, in New York, and in Chicago, engineers are laying something completely different. A pipe filled with liquid nitrogen at -200 degrees Celsius, carrying 10 times more electricity than a conventional power line, with zero losses. To understand why superconductors matter, you first need to understand why normal wires waste energy. Every wire has electrical resistance. Resistance means electrons collide with atoms as they flow. Every collision releases a tiny amount of heat. Multiplied across millions of kilometers of grid wire, it adds up to staggering waste. This resistance problem gets worse with heat. In summer, when electricity demand peaks, the wires themselves heat up from carrying high current. Hot wires have higher resistance. Higher resistance means more losses and more heat. A dangerous feedback loop that makes the grid most fragile exactly when you need it most. And then there is the overhead line problem. A conventional 380 kilovolt overhead transmission line needs a corridor 70 meters wide to operate safely. Underground HTS cables need 3 meters for the same power capacity. In cities, those 70 meters simply do not exist. Now the physics that makes superconductors extraordinary. In 1911, a Dutch physicist named Heike Kamerlingh-Onnes discovered that certain metals, when cooled to extreme temperatures, suddenly lose all electrical resistance. Completely. Not almost zero, exactly zero. Electrons flow through with no collisions, no heat, no losses whatsoever. For decades, superconductivity only worked near absolute zero, -269 degrees Celsius. That required liquid helium, which is expensive and rare. Then in 1986, IBM researchers discovered high-temperature superconductors that work at -180 degrees Celsius, cold enough for liquid nitrogen, which is cheap, abundant, and safe. Here is what zero resistance means in practice. YBCO can carry 9 million amperes per square centimeter. Copper manages about 1,000. YBCO carries 9,000 times more current in the same space. That is why one superconducting cable replaces up to 10 conventional ones. The cryogenic cable is an engineering masterpiece. Think of it as a pipe inside a pipe inside a pipe. The innermost layer carries the superconducting YBCO tape wound around a hollow core. Liquid nitrogen flows through that core at -200 degrees, keeping everything superconducting. Outside the superconducting core sits a cryogenic envelope, insulation that keeps the liquid nitrogen cold. It works like a thermos flask, but far more sophisticated. A vacuum jacket surrounding the cable reduces heat transfer from the surrounding ground to nearly zero. Installing these cables underground requires specialized engineering. A trench 3 meters wide is excavated. The cable is laid in sections and connected at joints. At each end, a termination station connects the cold superconductor to the conventional warm grid. The whole system looks like standard infrastructure once buried. The entire cooling system uses a small amount of electricity to run the refrigeration. But here is the key. The energy saved by eliminating resistance losses is far greater than the energy consumed by the cooling system. The net result is massively positive over the cable's lifetime. The first proof came in Essen, Germany. In 2014, the Ampacity project replaced a conventional 110 kilovolt cable with a 1-kilometer HTS cable operating at just 10 kilovolts. It carried the same power at 1/11 the voltage, eliminating the need for the transformers that had served that route. Across the Atlantic, Long Island in New York has been running a superconducting cable since 2008. The LIPA cable carries 574 megawatts through a 600-meter underground route. It has operated continuously in a live commercial power grid for over 16 years. In Munich, the Superlink project is taking this to the next level. A 12 to 15 kilometer superconducting cable connecting two major substations beneath the city will carry 500 megawatts at 110 kilovolts, making it the world's longest high-voltage superconducting cable when complete. South Korea's Shingle project boosted urban grid capacity without digging up roads for new substations. In 2024, Sumitomo Electric delivered 640 kilometers of HTS cable to China's Smart Grid initiative. The technology is no longer experimental. It is being procured at industrial scale. The technology is exploding now for one reason: artificial intelligence. In 2024, Amazon, Microsoft, Google, and Meta together spent $200 billion building data centers, a 62% increase from the previous year. These facilities need more power than the existing grid was ever designed to deliver. Microsoft went public in early 2026 with its research into high-temperature superconductors for data centers. Their statement was direct: as AI systems grow, power is the biggest limit. Superconducting cables deliver an order of magnitude higher capacity than conventional lines at the same voltage. Industrial adoption accelerated sharply in 2025. By mid-year, 35% of all HTS cable deployments globally were in industrial facilities and data centers. Fujikura in Japan launched a commercial YBCO production line capable of 1,200 kilometers per year. The supply chain is scaling to meet demand. There is another reason governments are paying attention: the grid's vulnerability to solar storms. In 1989, a solar flare knocked out power for 9 million people in Quebec for 12 hours. A Carrington-level event, the size of the 1859 solar superstorm, could destroy transformers and cut power for weeks. Underground superconducting cables are inherently immune to this threat. They are shielded from geomagnetic fields by the Earth itself. No overhead wires collecting induced currents. No exposed transformers. China has understood this and is aggressively building underground HTS infrastructure. The ultimate goal is room temperature superconductivity, a material that superconducts without any cooling at all. In 2023, a South Korean team claimed to have discovered it with LK-99. The claim collapsed under scrutiny, but the dream remains alive, and the physics does not forbid it. The power grid most of us take for granted is being quietly, invisibly replaced. Not above our heads, but beneath our feet. By 2032, the superconducting cable market will be 48 times larger than today. Will your city be one of the first to go underground?